So first off, it's going to be helpful if you make this graph over here. And this is one that you should be able to graph without a calculator all the way back to the first unit this year. Looking at this and seeing that its parent function is x squared. We had you memorize what x squared looks like. And we talked about the transformation rules. The plus 4 would shift it left 4. The negative out front would flip it over the x-axis. And finally, the minus 1 shifts it down. So if you think of those as individual steps, you should be able to reasonably graph negative x plus 4 squared minus 1 like so. That's the function we're working with. But it has this piece here. And in question 8, trying to get you to think about why it needs to be there. If you don't understand why it's there, then it's kind of confusing. So, I don't really want this whole function. I want this part of the function, where x values are greater than or equal to negative 4. So I want to ignore these. And the reason why is because without that restriction, it would not be what we call one-to-one. The one-to-one means it passes the vertical line test and horizontal line test. And that's important because if it's not always 1, the inverse would not be a function. Now, that may not seem like a big deal to you, but question number 1 is, what is the inverse function? So I can't ask you what the inverse function is if the inverse is not a function. So without this restriction, the inverse is not a function. So we have to put that in there and say, well, this has to be that. Okay. To find an inverse function, if this is its function, its inverse, all that means is you're switching input and output. So step 1, you should swap x and y. That's always the easy step. And then we like to solve it for the new y. And that can vary from one step, pretty easy, to multiple steps. This one is multiple steps. So you should have added the 1 over. You should multiply both sides by negative 1. Undo a square, you should take the square root. That could be plus 4 or minus. We really only want one of them. And then finally subtract 4. Now, sometimes it could be the positive square root of negative x minus 1 minus 4, and sometimes it could be the negative square root of negative x minus 4. It's almost always going to be the positive, but it depends upon this restriction. So how we determined which one of those it was, so that we're not just guessing there at the end, is if we know what the function looks like, we should also know what the inverse looks like. Because if the function has a point at negative 4, negative 1, the inverse would have a point at negative 1, negative 4, which just means swapping x and y. This point, swap x and y goes here. If the function has a point at negative 3, negative 2, its inverse would have a point at negative 2, negative 3. So at this point, swapping x and y. This was negative 2, negative 5, so negative 5, negative 2. Of course, you can copy over more points, but it helps for you to see what it looks like. There's several things going on here with the graph now. So even if you weren't required to measure graph, it's probably still a good idea because we talked about an inverse and its function as symmetry at y equals x. So this should be cutting that overall graph in half, and it does. So that makes me feel good about the graph. Because this is opening up, it tells me that the inverse was the positive of these. And to go even one more step, I think I know what the inverse looks like. And I think this is the inverse function. I can know beyond all certainty with the calculator. I can graph it and see that it's what I have for my inverse. This looks the same as this. So now I'm very, very confident that that is correct. I did a mistake. Written mistakes is something out of order. It's probably not going to work out like that. Okay, so that's probably the single most important thing. Understanding why this is here, how to find this, how to graph it, how it all checks, it all kind of connects together. So if you understand what you're doing, you should see how those pieces all fit. Okay. And there's also a pattern between the domain and ranges. So when I say only look at these x values, I'm actually restricting the domain of the function. Its x values is its domain. And since I have it graphed, I can look at its range, negative infinity to negative 1. And since I have my inverse graphed, so even if I didn't give you a graph, you would still want to graph it because then you could look at the graph and say, okay, it's, oh, sorry, I put that in the wrong spot. That is it. The domain of the inverse is negative infinity to negative 1, include negative 1. And the range of the inverse is negative 4 to infinity. So I can see all of that from the graph, assuming you know what domain and range is. But you also should have one more check built in here because of the pattern that it was supposed to be. If the difference between a function and its inverse is that you're just swapping x and y, then possible x's should become possible y's. Possible y's should become possible x's. These two need to be the same, and those two need to be the same. So the domain of the function compared to the range of the inverse should be the same. But it's not, something's off. The range of the function should end up being the same as the domain of the inverse. You're just switching x and y. So one more thing that kind of should come together as a check. Are there any particular questions you see in this group before we just change the function and look at another one? Yes. You mean from right here? Just based on, so I took points of this function and I switched x and y to get points on the inverse. Remember I did that? And the fact that this is pointed or opening upwards tells me that it was never flipped over the x-axis. If it's flipped over the x-axis, it would be like this. And that's how I know that it's plus. And when you have a calculator, you can always just graph it and visually see it as well. Alright, so now the other side. So again, this is why this has to do with radicals. The inverse of a quadratic ends up being a radical equation. Alright, so if we went the other way and we said, okay, here's a radical. Let's go ahead and graph it. So again, back to week 1. This was a parent function we asked you to memorize. This was a transformation left 2. And this was a transformation up 1. So with very little effort, you should have an idea of what the function looks like. course, it helps if you have some specific points, but you're also always a good idea to make a table. Because the table's not written there for you, feel free to plug in points and get it to be more accurate. Here's the function. Okay, so if I want to find the inverse function, I'm going to do this time here because I have more space. Inverse is where you swap x and y, you're swapping input and output, and then you need to solve it for y. So in this case, we would need to, it's going to solve differently than this one up here, because you're starting off with a different type of equation. So subtract 1 from both sides. You want to square both sides. And you want to subtract 2 from both sides. One, we've got one extra thing that we need to come back and think about that's not obvious to us yet. So, by doing the algebra steps, I figured out what the inverse function is, and you can go ahead and square this out. You can FOIL this if you want to. So remember, this is called vertex form, so you should be able to look at this and see that the vertex is at 1, -2. Or I guess you could have just copied over this point. -2, 1 becomes 1, -2. -1, 2 becomes 2, -1. 2, 3 becomes 3, 2. And then eventually, you see the shape of the graph, and it's okay to stay Remember, there's no questions about this. It is helpful if you see the line symmetry at y equals x, cutting the graphs in half. But here's where there's an extra thing to this that you may not think of that technically needs to be stated. If I graph this whole parabola, then y equals x is not cutting the graph in half. So since we're basically undoing what we did up here, we need to give this restriction. Only take the x values greater than or equal to 1. Only the stuff that I graphed. I don't want this part of the parabola. Okay, so just getting the graphs correct should be enough information for you to get these. This would be -2 to infinity, although this information is also right there, but I see it from the graph as well. The range is 1 to infinity. I can see that basically only from the graph. The domain, or the inverse, I'm pretty sure that's the correct inverse because it looks like it has some right line of symmetry. So now I'm confident to say that the domain is x values 1 to infinity and y values -2 to infinity. And you probably wouldn't have a question like this on the test because it's kind of hard to come up with a question like this. But you should have this checked. If x's become y's, the domain of the function should be equal to the range of the inverse function. And y's become x's, so the range of the function should be equivalent to the domain of the inverse. So I'll just assume that as a way to write down the answers very quickly. Use it as a check. Okay, this one has a slightly different restriction. I didn't have to say take the x values greater than or equal to -2. I guess I don't even really need to put this here at all. But because this is already 1 to 1, it's not the same reason as question A. But you can only plug in x values of -2 or bigger because otherwise you would take the square root of the negative number. And we can do that and get imaginary numbers, but imaginaries, it's implied that we're not talking about imaginary. We're graphing and graph imaginary numbers. Domain and range is talking about real numbers. So if you plugged in anything less than -2, you would be taking the square root of the negative. That's why that part of the graph does not exist. But I guess technically it kind of goes without saying. We don't even have to list that out. Okay, so quite a bit of overlap from this, but something with a different function made some of it kind of play out a little bit different. So, any specific questions from 9 through 16 you want clarification on? Alright, and then finally, down here at the bottom, in order for two functions to be inverses of each other, the way you would prove this is through what we call composition. So composition, remember, was that little open circle. O, it's really not an O. Also kind of like times, it's not really a times. So this is when we talked about if you plug G into F, it simplifies to X, and the mathematical definition says that also if you plug F into G, it would also simplify to X. So we did compositions at the same time because this is how you prove that two functions are inverses of each other. You have to say plugging one into the other simplifies to X. Or you can write it like this. If you don't like the composition symbol, you can show that you're plugging G into F this way or F into G that way. So F into plugging these two.